Welcome to the Gravity Notes, as per Colin's notes. He publishes these each year. These are the 2020 Gravity Field Notes. You should have a copy of these on OneNote, on Compass, and I gave you a hard copy in class as well. So, today we're going to talk a little bit about gravity and basically what it is. As you can see, these notes have been adapted from the pre-2016 study design. So as you can see, a lot of this stuff has been lined out because it no longer applies to the current study design. That's not that important. Everything else is in there. I have also included a beginning to a help sheet, which I produced for you and uploaded as well. So you can see a lot of stuff is on here. And don't forget, you do really need to have your help sheet right next to you the whole time, scribbling every little thing that is important onto it as you go. Okay? So this video is going to be a little bit about the notes, the gravity. As you can see, we're going through here. Colin, as all physics people, love to chuck in their own bit of humour here, or jokes that they found somewhere. The colonisation of space. Well, what this really is about is Newton's law of universal gravitation. Okay, and the reality is that Newton understood gravity well enough to be able to make some really stunning predictions about the motion of the planets and objects near Earth, and wrote down a whole bunch of math that eventually became Year 12 methods specialist and physics. And so you've got him to thank for doing all of that in his early 20s, back in the, I think, was it 1600s? I think, not great with dates. Anyway, basically this is a study of the law of attraction of masses of bodies toward each other. It turns out that there's not really an attractive force, an attractive thing that is happening between masses. The reality is that, and this is something he didn't know, that objects move through basically space-time, and objects with a huge amount of mass tend to bend space around them. And this was all confirmed experimentally a few years after Einstein proposed it and changed our entire view of the universe. So he's the one that sort of kind of fixed the problems with our understanding of gravity so far, when it came to objects that are either really, really small or objects that are incredibly far apart, and where these laws of attraction, F equals gmm on r squared, is one of the most important results. So the reality is, it's far more complicated than what is required for this course, okay? And there's a lot more math in it, but as far as what you need to be able to get through this section of the work is an understanding of the formulas that govern this kind of motion and how to manipulate them. Okay, so I'll run through a little bit of these notes, but then the main value in this will be going through the 80 odd examples that there are with this video, in these notes, and a lot of which I want to do on the video for you as well, just to make sure you get your heads around what's important, what's not important, that sort of thing. All right, so basically the force, okay, so what have we got here? Newton's law of universal gravitation. Gravity is a force that exists throughout the universe. It makes things fall down when you drop them. It keeps satellites in their orbits. It leads to the tides of the Earth, causes stars, black holes to form, and will ultimately determine the fate of the universe. All right, Newton determined that gravity is a force of attraction that exists between any two bodies. Now, as we just discussed earlier, There is no actual force, but it behaves as though there is. In fact, any two objects that have mass will exert a gravitational force of attraction. Gravitational forces are very weak and only become noticeable when at least one of the objects is extremely massive. And that's part of what makes gravity really hard to study. Alright, so this is the main formula here. So what we've got here is what you would ordinarily see here. This F equals mg is really F equals ma, but we just substitute g for a when we're talking about objects near the Earth or anywhere actually in a gravity field. So g is just acceleration due to gravity, so we change that for mg, and then what we do is take that and say, okay, that is the same as gmm, worst m ever, gmm on r squared, okay, which basically means that what we have here is acceleration, g equals gm on r squared. So as you can see, this here is acceleration due to being near a particularly large mass. And when you multiply that by the actual mass that you are dealing with, whatever that is, that's when you've got basically F equals ma. So you can see this here really is acceleration, and all this really is F equals ma in a different form. Okay, so I don't know if I explained that very well, because like videotaping yourself is incredibly like nerve-wracking. Now, what we're going to do is have a quick look at what g is. As you can see, we have in the notes, we have g. This is the universal gravitational constant. Okay, so this goes on your help sheet. See? Put it on my help sheet right at the top, just to make sure you never like write it down wrong or accidentally, mess it up. So what it is basically there's an experiment done to try and determine what the actual constant was. There was a relationship between two objects that they found was attractive, and so the force exerted by two masses are proportional to how big they are, and the gravitational constant is what links them together into a proper equation. So I'll draw this nice and big for you, right? It's nice and big. 6.67 times 10 to the negative 11, so it's a tiny, tiny little number. Newtons, meters squared per kilogram squared are the units, okay? They're not something that you need to have in mind all the time when you're doing this work, but occasionally there are questions out there that leave this as a bit of a hint that they're talking about the gravitational constant, okay? So always write it down if you're going to be using it. It's really important to have that there. The units for gravity are the same as the units for acceleration, but what you'll notice is we use two different versions in this chapter. So traditionally, acceleration, which in this case is gravity, has the units meters per second squared, which I normally write. But if you think of how you can calculate acceleration, acceleration is just derived from F equals ma. And if you go and solve for acceleration, you have A is equal to F over m. So if you follow that through with the units, newtons, so moving on. Gravitational fields. For a body on or above the surface of the Earth, the mass of the Earth may be considered to be concentrated at its center. The formula for gravitational field is found by giving the gravitational force by the mass of the smaller object. So, in this case, this calculation is simply to calculate the field strength itself, okay? And the field strength depends heavily on how far away you are from the center of mass. So from the center of mass is where you take all of your measurements. So if I were, well, let's see what this diagram has here, okay? So here we go. These are gravitational field lines. We've discussed this in class before. You've drawn some notes as well. Gravitational field lines always act down. They're always attractive. And there's no such thing as a gravity field line going the other way, okay? So gravitational field lines of the Earth, the field strength, the same rules for field lines apply. They never cross, and they also are weaker where they're more spread out. So how do they weaken? Well, as Newton showed us, the force is proportional to the inverse squared law, okay? And that was what he and, what Edmund Halley and Newton ended up predicting the path of Halley's Comet. And so they both got like super famous off of that discovery, because until Halley went and visited Newton, nobody knew what a comet was, where it came from, whether it was something that was coming, whether he was seeing the same comet over and over again. And it was Halley that went and spoke to Newton at his university and said, what can you tell me about this? And Newton had already worked it out. And then Halley made a deal with him, helped him publish his work, which then went off to become Year 12 maths and physics, and the rest is history. So there are a whole bunch of different iterations of these formulas. So the acceleration, let's see, the force between two bodies equals the weight of the small body. Thus, the acceleration due to gravity at the surface of the Earth, g, is determined by the mass of the Earth and the radius of the Earth, not the size of the mass in the field. To calculate the value of g at the Earth's surface, basically, you apply the formula, which is great. Physics is always gives you always a nice little toolbox of things to do, to use when you need to do a calculation. There are several common errors that students make doing these calculations. The most common is to forget to square the bottom line, which is hilarious because, I've marked a lot of sacks in the past, and you can see that everyone writes the squared in, not everybody actually presses that button in the calculator. Okay, really important that you meticulous in your calculations, especially with gravity, because the numbers are enormous or tiny, which means you're using a lot of scientific notation, you're pressing a lot of buttons in your calculator, you do not need to mess them up. Alright, so this is where we derive our 9.8 meters per second squared. Okay, here is an interesting graph. Alright, this graph shows the gravitational field strength, newtons per kilogram of object, from the center of, let's say, the Earth, okay? And this one is specifically about the Earth, it says so. So from the center of the Earth, if you could drill down to the center of the Earth, sit right down there, you would end up basically floating. There'd be zero gravity at your spot because, why? Well, every bit of mass around you is distributed evenly, so every sort of vector, all of the vector sums of the forces are cancelling each other out. So the sum of the forces at the centre would be zero, and that kind of explains this graph here, where it starts. You have zero gravity at the very centre of the Earth. This here is the surface of the Earth. Now this graph is kind of important, and I added it to your help sheet down here with not only what's in these notes, but also a question which came out of last year's exam that was not done very well by most people, and it was simply through a lack of understanding of what this graph meant. Okay, so as you can see, the force of gravity is linear until you get to the surface of the Earth. Why? Because as you move from the centre of mass up to the surface of that mass, you are experiencing forces both above you and below you. So they all add up resulting in a nice linear change in the force of gravity that you experience as you move from the center to the surface. Now, when you get to the surface, that puts all of the mass below you. So at that point, you reach gravity 9.8 for the Earth, and all different things depending on what object you're sitting on. Now, when you leave, though, as you then leave the surface of the Earth, the force starts to drop, and this is what this F, the force, is proportional to the inverse square of the radius. Now, as you leave, it drops exponentially, okay? And until the point where it becomes immeasurable. We assumed, or with the theory is that every piece of, a theory that I've heard, is every bit of mass or matter in the universe pulls on every other bit of matter, because at no point can you get so far away that this result here is zero. So, mathematically, it says that every bit of matter applies a force to every other bit of matter in the universe, but again, another one of those things that's impossible to measure, and there's lots of sort of work being done in trying to figure out, is that actually true? Is the gravitational constant actually the gravitational constant for objects that are really, really tiny or really, really far away? So again, these are all things that are still being debated. All right, but for Year 12 physics, don't need to worry about it. The gravitational constant is 6.67 by 10 to the negative 11. Newtons meters squared per kilogram squared. And that's all you really need. So, satellites in orbit. Okay, one more thing. The area under this graph is really important. Okay, so the area under this graph tells you how much gravitational potential energy an object has per kilogram of that object. So, this was the biggest problem with that question that that our kids got last year in the 2019 exam. The biggest problem was that a lot of people didn't realise that the area under this graph was actually gravitational potential energy. So it's joules is what the answer comes out as. It's in joules. And the fact that you were provided with a graph in that question, a lot of kids ignored that graph and tried to work things out in a sort of a little hodgepodge way of applying formulas, completely ignoring that as you move away from, as an object moves significant distances away from the mass, from the gravity mass, this 9.8 doesn't apply. So there's no point trying to calculate potential energy changes using 9.8 when you're moving, say, from this far from the Earth's surface to this far from the Earth's surface. This is 9.8, it's nowhere near correct. And that's why you need to fall back on the whole area under the graph. If you do that, then it's actually a really easy question, okay? Whereas if you don't know that, it's impossible. All right, satellites in orbit. Okay, a satellite is any object. Okay, so the moon is a satellite. I'm sure you know all this. Any object in orbit around another is a satellite of that object. Okay, so the moon is the Earth's only natural satellite, but we also put a bunch of artificial satellites out there around us. Okay, let's see. This here becomes, the force of gravity holds the satellites in their orbits and causes them to have an acceleration towards the central mass. Now this is where all of your work in circular motion overlaps beautifully with gravity, okay? You'll notice in circular motion, you probably remember from circular motion, these formulas here, okay? So these formulas here all still apply. Okay, and what even better, you can actually substitute them into your gravity formulas to make all sorts of calculations. Okay, so this is where you hit pause and you type everything in. Okay, so not type, but write everything on your help sheet. Okay, so you need these formulas. A equals v squared on r. V, which is v for velocity, is equal to 2 pi r over t. Okay, so this is a circular motion formula, this is a circular motion formula, and because orbits are essentially circular motion, they all apply. Acceleration can also equal, and sometimes I like to, when I'm making up my own sort of help sheet, 4 pi squared, I'll just equate them as if these are all acceleration, I can just make them into one nice long line. So I know what goes with what, okay? And then also here, g, acceleration, you can also add in g, which is the same as acceleration, at a particular point away from the gravity mass is, where are you? Yeah, g, yeah, obviously g m on r squared. You'll notice, also f equals mg, ma, all of these are also true. Don't forget sort of f equals also g m on r squared. Let's just really quickly, can you see that? Did I just draw like right off the screen? I did, I drew right off the screen. Okay, let's just turn this a little bit so you can see what I wrote. All right, now what you can see here, I hope, if it's bright enough, is, what you can see here is f equals gmm on r squared. Now, what are these m's? So, I like to imagine, the way I learnt it, I like to imagine that big M, okay, is always the larger mass. It makes no difference, obviously, but that's just how I do it. Larger mass. This would be the smaller mass. Okay? And this here is really important that you understand how this works, because it's a lovely little trap that is left for you in a lot of your questions. And that is, for example, the r is the distance between the centre of one mass and the centre of the other. That is what r actually is. So if I draw that for you, large mass, smaller mass, doesn't matter. One doesn't have to be small, they could be the same, it makes no diff. But if I put a dot there, and then join them with a line, that distance from the centre of one to the centre of the other, that is r. The only time that becomes a problem is when they give you the word altitude, all right? If they say altitude, they're trying to get you, okay? There's no other way of putting it. They're just trying to suck you in. Altitude is very specifically the distance between some satellite or object in orbit and the ground, okay? That is altitude. So anytime you hear the word altitude and you need to apply these formula, you need to add the actual radius of the object itself, okay? That's really, really important. That often comes up in calculations involving this here, okay, this formula here, where you'll be given altitude and asked to calculate what's the gravitational field strength at, you know, at this altitude, say 600 kilometers, all right? So of course 600 kilometers becomes 600,000 meters, okay, because we don't use kilometers in physics, all right? And you then also need to add the radius of the Earth, which is about 6,400,000 meters, okay? All right. And all of that is, these are all standard values, just like as discussed earlier when we were talking about electric charge and how there is a elementary charge, okay, which is, you know, we just assume every charge in the universe, every electron has the exact same magnitude of charge, and that's what we call the elementary charge. Well, the radius of the Earth is a known value, the mass of the Earth, the mass of the Sun, the, you know, average orbital distance. All of these are just values that you can take, like, I guess, like pi, all right? So they're just known values that you can always apply. All right. Now, what's next? Gravitational potential energy. Oh, okay. So here, this section of the notes actually goes into a bit more depth on what I just mentioned earlier about that question that wasn't done very well last year, and that was where students didn't. Pardon me. Students didn't understand that this here, the area under the graph, is your gravitational potential energy, and so whether you can calculate it using a triangle, or whether it's a triangle or sloping line, or whether you have to count squares, doesn't matter. You basically area under the graph that resolves those questions. So an object moving away from the planet gains, well, let's see what it says here. As an object gets further above the Earth, it has gained gravitational potential energy, so it must lose kinetic energy. Okay, an example is the space shuttle. The rockets provide thrust and the kinetic energy is converted to gravitational potential energy. If the satellite starts some distance from the Earth and falls towards the Earth, then it has lost gravitational potential energy and hence it will have gained kinetic energy. An example is a meteor that is plummeting toward Earth, gaining speed as it approaches. Okay, Kepler, old man Kepler. 1609. Kepler, German astronomer, published his 3 laws on the motion of the planets. Okay, I don't believe the 3 laws are actually specifically ever really specifically referenced in this course, not from memory anyway. Basically, this is one of the last things that you really have to, yep, here you go, this is where the examples begin. So this is one of the last things that you have to really get into your head, all right? And again, I stuck it on the help sheet. Again, students have it on the help sheet, get a question like this on a SAC or an exam, still got no idea how to do it, all right? Why? Because you've got to do questions. There's just no way around it, all right? You need to experience what it feels like to calculate these things. You can't just chuck it on your help sheet and not actually apply it. So this is kind of, you can see the derivation here, and rather than me just running through it, you can quite easily read it. The derivation is really, really clear, but the essential idea is this though. If I have a mass, an object orbiting around it, okay? So I've got an object orbiting around this mass, okay? It will have a certain radius of orbit. Okay, so this is my little object, my little satellite there. It'll have a certain radius of orbit, and it will have a certain period. Okay, so it'll have an R, and we'll call this object A, all right? So A will have a certain radius, and it will have a certain period of orbit, period A, okay? It will take a certain amount of time to get around. Okay. Now, if I put another object around the same mass, whether this is the Earth, the Moon, the Sun, doesn't matter, okay? If I put another object around here and then do the same sort of measurements, so here I've got R, this is object B, so object B has an RB, so a radius of orbit B, and it has a period B, which is the time it takes to get around one time, okay? That's what all of these here, that's why we often use T in these periodical calculations, because time's otherwise meaningless if you don't narrow it down to revolutions. Anyway, now what Kepler figured out, which is like really cool, is this beautiful little idea that R cubed over T squared is a constant. And what that means is, if I take the radius of object A and cube it, okay, again, fraught with danger chucking these huge values in your calculator, being really, really careful. Stop using your CAS calculators, those of you that are still doing that, okay, over the period of A squared. If I make that calculation and come out with a specific number, I will find, if I do the same thing with object B, that I will always get the same number. Okay, so these two values, even though this value, this T is much bigger than this T, and this R is much bigger than this R, when you cube and square and make this calculation, you find the number that you get out of this is always the same. Hence I draw it equals right there, which is what that means. All right, so that means that there are a couple of classes of questions that you can get when dealing with this kind of thing. And one of them is simply, you'll be given the radius of orbit of one object, the period of the other object, and either the radius or period of the other one, and asked to solve for the one thing that's missing. Super easy, really, really simple idea. But that's one sort of family of questions that you get, right? There is one other, and it is nailed down to this. I want to draw it over here, make sure you can see it. Make a little space. this is the other formula, and that's why I was very careful to put it on your help sheet for you, just to make sure. Gm, and this comes from this derivation here. This is super useful, all right? Gm on 4 pi squared is equal to r cubed over t squared, okay? So that needs to be there. Now, what's interesting here is we say that this value is a constant, but it isn't really a constant. It's a constant for the particular object that you're in orbit around. So it means if you are in orbit around the Earth, it will be a certain number. That number is set by the universal gravitational constant multiplied by the mass of the object that you're orbiting, big M, divided by 4 pi squared. Pi is a constant, 4 is a constant 4. Okay, so all of this, if you are only talking about objects orbiting a particular body, this whole value is a constant. It is one certain number which is affected by M, big M, for the Earth. It's a different number for the Sun. It is a different number for the Moon or any other object. But for every object that you put in orbit around that particular thing, whether it is the Sun, the Earth, the Moon, or whatever, that number will always be the same for all of the objects that are in orbit around that particular object, okay? So this here is really, really useful because there are the other sort of family of questions that you're asked to do in regards to Kepler's law is calculating, well, if this is the orbital period and the radius of a particular object, how much mass does that object have that they're orbiting around? So you can solve this. And again, you go to your help sheet because you make sure that you can solve this for pretty much the only other thing they can ask you for, which would be the mass of the object that you're orbiting, which in this case would be, so r cubed over t squared is just sitting there. We're going to put 4 pi squared there and drop g down here, and you have the formula that you need to solve for the mass of the object that all of these things are orbiting around, whatever that may be. All right, so that is, they are the two classes of questions that you will ever get for Kepler's law. And there is only one other thing when it comes to Kepler's law, which is like good to keep in mind. And it's best shown with an animation, which I just so happen to have already queued up. And this is it. That's not it. This is it. This here is an object in orbit, elliptical orbit. Most orbits are elliptical, unless there are a few circular orbits, but they're out in the universe naturally occur, but it's incredibly rare because the mass of the orbiting object, the mass of the object that you're orbiting around have to be like just right, and you end up with beautiful circular orbits. But anything changes, then it pushes itself out into an elliptical orbit. The Earth is in an elliptical orbit around the Sun. So when we talk about the radius of orbit of the Earth around the Sun, you're often talking about an average, just to sort of, I guess, dumb it down so we can do some basic maths with it. All right. So we take the average. The reality is that it is elliptical, but only just, okay? But if you have a look at I can't find the word, don't worry about it. Here, this. There's a couple of things you need to notice here. First thing is that this ellipse, the way an ellipse works, or an elliptical orbit works, is there are two focal points in an ellipse. Now, hopefully that came through clear in the video. Looks like it did. There are two focal points. Guess where one of them is? Obviously, right in the middle of the Sun there. This is the Sun because it's yellow. All right, so there is another focal point for an ellipse, which is exactly kind of the same distance away from the other end of the ellipse, the other long end, okay? There's nothing's ever at that point, okay, in these cases, all right? And so when you're looking at this, you've got two focal points. One of them is the object that the other object is orbiting around, the other one is empty. Okay, so that's how it's all set up. That's one thing to keep in mind. The other thing to keep in mind is watch the speed of the orbiting object. Notice it's slow out here and speeds up around here, okay? That's important, all right? Because there is one other set of questions you can be asked, and that is, at which points in this orbit is the kinetic energy the greatest, and where is the gravitational potential energy the greatest? So, obviously, kinetic energy is linked to its velocity, and therefore, highest velocity is at this point here. So this is where EK is a max. Over here, this is where UG is a max, all right? And conversely, UG is a minimum here, and kinetic energy is the minimum there, okay? So keep that in mind. That also needs to make it on your help sheet, because it's something I've just explained, you will have just watched it, and then you'll completely forget about it, and then of course it's going to pop up in a sack somewhere, all right? So really important that you keep that in mind. This thing is not traveling in an elliptical orbit, it's not a constant velocity. It is speeding up and slowing down the whole time, okay? In fact, if you, let's see if I get this, explain this well enough. If you take, how does it, if I do a line to the middle here and a line to the middle there, and then a line to the middle here and a line to out here, okay? These map out areas, if you think about it, okay? The time to get from here to here is the same as the time to get from here to here, all right? So what that's telling us is that the areas traced out by the orbiting object as they move around, the area of this segment here is the same as this, okay? And what that basically alludes to is the fact that the energy in the system is constant, which is why, as long as nothing changes, okay, if this is some kind of comet and it's losing mass because of its long tail, and particles are being blown off it constantly over hundreds and hundreds of years, as it loses mass, it changes things. But if nothing were to change, this is basically a closed system where energy is conserved, and even though the kinetic energy and the gravitational potential energy can constantly seesaw between each other, which one's the maximum, which one's the minimum, the total energy of the system never changes. All right? Is there a change in momentum? Well, yeah, there has to be. How do you know if there's a change in momentum as this object orbits? Well, it's speeding up and slowing down. It's also changing, even though it also has a changing velocity, okay? So changing velocity implies an acceleration. If there's an acceleration, it means that there is an unbalanced force acting. Which way for an object that is moving in orbit, what are the forces? Now, you remember way back when we did some circular motion and a bunch of you didn't draw a good enough diagram in your help sheets, okay? And then some of you got this question wrong, okay, in the SAT. Well, here we go again. There is only one force acting on an object that is orbiting another object, and that is the force of gravity acting towards the middle there. There is only one force. So they are going to try and get you to think, oh, there's centripetal force. Oh, that arrow is not really good, but you know what I mean, right? Centripetal force, and they'll talk about all sorts of things. There's only one. There's just the gravitational force, attractive force acting towards the center of the object that you're orbiting around. That is it, okay? There's only one arrow, and it only ever goes one way. All right, so try not to get sort of sucked in by that. The question never really talks about elliptical orbits. It's always circular orbits to keep it nice and simple. Okay. I think that's it when it comes to sort of the lecturing part. And what we've got now is the questions, and there are 80 of them, would you believe? Okay, so what I might do is film this bit differently, okay, so that you can really see what's going on here. Yeah, all right. Goodbye from. See, every YouTube thing has to have a gimmick, right? So this is mine. This is like Simon Bobblehead. Hey, how cool is that? Like I've ever worn a tie to school. I don't know. All right.